Welcome to KINE2253, Motor Development Across the Lifespan. This lecture will discuss the third chapter of Lifespan Motor Development, the 7th edition by Haywood and Getchell. This lecture will provide supplementary examples and explanations to help provide a deeper understanding of the book chapter.
In this lecture, students will learn about biomechanical principles of motion, learn about biomechanical principles of stability and balance, and we'll discuss how an understanding of the principles of motion and stability allow us to study behavior across the lifespan and across development during the performance of motor skills. Learning to move involves learning the physics of your body. This is not an easy task because, 1, during development, your body is still growing. So once you may have mastered a skill at age 10, when you go through puberty and you grow 4 inches or so, now you have to adapt your movements for a bigger body, with longer limbs and potentially larger muscles. Second, you have to learn to move in different environments that cause you to have to adapt your movements. For example, learning to walk on sand or ice. Third, you have to learn to move with different movement goals. For example, throwing for speed versus throwing for precision versus both. Let's start a discussion of biomechanics, or the physics of the human body, by discussing Newton's 3 laws of motion. We move in an environment that has gravitational force. This force pulls a body or object with mass back down to Earth. The phrase, "what goes up must come down," means that if you project an object, including your body, away from the ground, gravity will pull you back towards the ground. As a result, the path or trajectory of that object or your body will move in an arch, or more appropriately, a parabola. Here I am showing you a child jumping. He projects himself with a certain amount of force at a certain angle. That's the dotted arrow on the left. That force can be broken into the force going up and the force going towards the right. At the top of the parabola, the gravitational force cancels the projection force. The gravitational force will then bring the body back down to Earth. The gravitational force is pointed straight down. The other arrow on the right is the projection force. Since the projection force moving towards the right is not subject to gravitational force, the body will still move towards the right. The net force is a dotted arrow on the right because it's the sum of the forces in each direction: the downward force due to gravity and the rightward force due to the projection. Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion until that object is acted upon by a force. In other words, to move something or to stop something from moving, you have to apply a force. For example, the football player on the left needs to apply a force on the tackling dummy in order to move it. The picture on the right is called Newton's cradle. This object illustrates Newton's first law, because in order to move the 4 balls to the right, you must first use the ball on the left to apply a force. This object, Newton's cradle, also illustrates Newton's other laws, which I will discuss in the subsequent slides. Newton's second law states that the force is equal to the mass of an object times acceleration. Alternatively, you can rearrange the equation to define acceleration as the force divided by the mass of the object. So the change in velocity, or acceleration, of an object depends on how much force is applied and the object's mass. So given the same amount of force, a light object will accelerate more than a heavy object. And in order to accelerate those 2 objects at the same rate, you need to apply more force to the heavy object. Another application of Newton's second law is that when you apply a force over a greater distance, you increase the total force applied. As shown in the cartoons on the bottom, if you take a step when throwing, you increase the linear distance that the force is being applied, and thus increase the total applied force. Another example is using a preparatory wind-up, which increases the angular distance over which the force is applied. In addition, a preparatory wind-up is also useful to cause a muscle stretch. That stretch in the muscle not only increases the distance over which the force is applied, but also mechanically loads the muscle like a spring, allowing it to generate more force. There is a trade-off between stability and motion. By definition, stability is the resistance to motion. For example, the child on the left does not take a step while throwing. He is more stable because both feet are on the ground. However, the child to the right takes a step, and although he is less stable, he is able to generate more force because he's able to apply the force over a longer period of time during which he takes that step. Newton's third law states that every action has an equal and opposite reaction. For example, as the baby takes a step, he exerts a downward force due to his mass times the gravitational acceleration with the front foot. This is the large solid black arrow on the right. This force is counteracted by an equal and opposite force from the ground pushing up on the foot. This is also called a ground reaction force, and this is indicated by the large dashed arrows on the right. The baby's back foot also exerts two forces. One force is downward, again due to gravity and the mass of the body. This is indicated by the small solid black arrow, as well as a force pushing backwards to push the body forwards. This is the green arrow. The opposite reaction is the ground pushing back up on the foot, again called the ground reaction force, and this is indicated by the small dashed arrow on the left, and a force pushing forward against the foot. This also is called a friction force, which typically prevents slipping. This is indicated by the red arrow. Remember Newton's second law. Force is equal to mass times acceleration. In this case, the downward force of the body equals the body mass times the acceleration due to gravity. So what happens when the force due to a person's body mass times the acceleration due to gravity is not counteracted by the ground reaction force? Essentially, you would fall through the ground. Another application of Newton's third law is the way in which our bodies naturally compensate for different segmental motion. For example, when we walk or run, there's a compensatory movement on the opposite side of the body. So, when I take a step with the left leg, this results in a right arm movement. Similarly, when you twist your lower body, this results in a counter twist in the opposite direction for the upper body. Before moving on to the next section, let's just recap. Body movement is governed by physical laws or mechanical principles, and we call this biomechanics. Newton proposed 3 mechanical principles to describe motion. Newton's first law states that an object at rest stays at rest, and an object in motion stays in motion until that object is acted upon by a force. Newton's second law states that force is equal to mass times acceleration. Newton's third law states that for every action there is an equal and opposite reaction.